Lab 4, Magnetic Bracking with Faraday by Justin Siegel. So, the purpose of this experiment was to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet and tube interaction computationally, and compare the computational results with the experimental or observed results. So, the main principles used in this experiment were Faraday's law, seen in the top left, the Biot-Savart law, seen on the bottom, Ohm's law, seen in the top right, and Newton's third law, which says every action has an equal and opposite reaction. So the computational time for the magnet to get through the tube was 1.13 seconds, and the experimental time was 1.21 seconds. The main assumptions made were that the magnet is a magnetic dipole, air resistance is negligible, and only forces acting on the magnet are the magnetic force and gravity. So for this experiment, the system is the magnet, the surroundings are the aluminum tube and everything else. The initial conditions are that the magnet is held above the tube and that there is no magnetic force before the magnet is dropped into the tube. So the procedure for this experiment is using the magnetometer app. The north and south ends of the magnet were determined. The magnet was then dropped into the aluminum foil tube, and the time it took to exit was recorded. This was repeated 5 times, so an average could be taken. We can't use something like a Ferris tube or a steel pipe in this experiment because it contains iron, which would make the tube an induced dipole, which would interfere with how fast or slow the magnet travels through the tube. And the magnet falls slower through the tube than in free space due to the induced current in the aluminum tube, which creates an upward magnetic force. So here are our results. Here are all the values for the tube, the magnet, and the time value average of 1.21 seconds. Here are our computational results. First, the geometry of tube was entered into GlowScript, then the bar magnet information, then a function to find the magnetic field of the bar magnet. Next, a function to find magnetic flux, the current in the ring, and the B field at each ring. Then the equation to calculate the next net force, and finally, 2 lines to update the magnet's velocity and position. Here at the bottom, you can see the final results, the red ring going clockwise and the blue ring going counterclockwise. And as you can see in the velocity versus time graph, at first the velocity exponentially decreases in the negative direction, then increases in the negative direction, then slowly decreases until it's constant for most of the experiment, but then once again exponentially increases in the negative y direction at the very end. So for this, if the system was flipped, the magnet going in the opposite direction, nothing physical would change, just the B field and the induced B field would flip. The total times were pretty similar, as the computational was 1.13 and the experimental was 1.21. But to make this more accurate and closer together, we would have to either split the tube into more rings or repeat more trials until we got closer. So for the additional questions, for the first one, the induced current would increase, and due to that increase in the induced current, there would be a larger magnetic force pointing in the upward direction, so the magnet would in fact fall slower. Now for the second question, it's actually the exact opposite. The induced current would decrease, which means magnetic force would decrease, so there's less of a force pointing upward, so gravity would do more work, pushing it downward. As seen as in third bullet, the magnet would fall faster. So overall, the main sources of error are the unaccounted for forces, such as friction or air resistance, or human error, which could be my fault in timing or measurement miscalculations. So overall, the experimental being 1.21 and computational being 1.13 results were very similar, which means overall there was minimal error, but that error did come from air resistance in the real world example that I did not account for. Also, the bar magnet does in fact act as a good dipole. And finally, the aluminum foil produces almost no external magnetic field. Thank you.